Hello and welcome to this presentation on DirectX11 transformations, camera, and terrain. Much of what we'll do in this presentation is organizational changes. We'll modify or reorganize the code, the C++ part of the code, so it might be a little bit easier to work with. Just as a review, we'll look at the different types of transformations that we have. One way of categorizing them is to separate them into world, view, and projection transformations. The world transformations are largely made up of three basic types, and those are translation, scale, and rotation. And you should also be on the lookout for a separate presentation on DirectX11 Math, where we talk in detail about how combining these transformation matrices using matrix multiplication to get different transformation effects. And when we do combine them, the order in which the transformations are combined is very important because matrix multiplication is not commutative. One of the first things we'll look at today is to organize some of the code involved in the view and projection matrices into a camera class, a C++ camera object. And we have the diagram on the right of the so-called view frustum, and it's almost looks like a pyramid or part of a pyramid with maybe the pointy top cut off. And part of the camera properties are position of the camera, the look at point of the camera, and the up direction of the camera. And you can see in the diagram here, the position is placed here, the look at direction is this is the point in space that we're looking at, and then of course the up direction here gives the camera's orientation. When we combine these pieces of information together, we can create what we call a view transformation. So we'll make it the responsibility of the camera class or the camera object to keep track of these and to produce a view transformation for us when we need it. The other part is the projection transformation, and this has to do with the field of view. And the field of view is generally either the angle between the two sides of the viewing frustum or the angle between the top and bottom plane of the viewing frustum. And different libraries specify it differently, but it's generally the angle in one direction or the other. The aspect ratio is the screen width to height ratio, and again, maybe it's height over width, maybe it's width over height. It depends how the library defines it. And then we have this concept of near and far clipping planes. If you recall, we have a depth buffer or Z buffer that's used in rendering that we looked at in a previous presentation. And the near and far clipping planes, they specify the Z value. The near clipping plane specifies a Z value that anything in front of that near clipping plane will not get rendered, and the far clipping plane is a Z value where anything beyond that will not get rendered. And so the depth buffer resolution will be in between these near and far clipping planes. Something else we'll look at as we build our camera object or camera class, and I believe we've seen this in a previous presentation, is a function called getAsynchronousKeyState. So when we get input from the user in Windows programming, we have a couple of different options. One is we can respond to a user to a Windows event or a Windows message, or every update, every frame, we could pull the hardware, like the keyboard, and ask what is the state of the keyboard. And for some inputs, Windows messages work better. For example, if we want to toggle wireframe mode on and off, the Windows messages can be a better option for that. For movement of a camera and for some gameplay actions, the get asynchronous key state can be better, because we can ask, in a single update, we can ask several questions. Is this key pressed? Is that key pressed? Is this mouse button down? And so on. Whereas in a Windows message, we generally get one of those messages per update. There's advantages and disadvantages of both, and sometimes it's useful to try them both out for a particular action within a game to see which one works better for users. We'll start out by creating a camera class, and this class will have a variety of properties that we've already discussed: the position, the look point, the up direction, field of view, screen width, screen height, near and far clipping planes, and then some capabilities that we might want to use, and that is to be able to ask the camera to give us the current view and projection matrices, to rotate the camera viewpoint so that we can look left, right, maybe up and down, and to move the camera forward, back, left, right, depending on your application. So let's get started with that. We will start out with some code that we've seen in the past. This is basically from previous presentation where we just made a triangle, a vertex buffer with a single triangle. This is actually the same triangle being drawn, but it's being drawn with different transformations. So the smaller one in the center is being scaled to make it smaller, and then the larger one that's rotating is scaled by a different amount, so it's a different size, and it's also translated out and rotated, but I guess in the reverse order. It's being rotated first and then translated out along the x-axis. When we look at the code for this, especially the data members of the application class, we can see that there's the vertex position and color, and we can see that objects for the vertex and index buffer, screen width, screen height, viewport, camera position, all these are variables in our application class. So I think it might be useful to take the camera position and maybe define some other camera properties, and maybe to take the screen width and screen height, possibly even the viewport, and move them into a camera class. So what we'll do is create a new header file, and we want to put it in the source folder with the other we can just call it camera.h. And we can either use this pragma once or pound define compilation directives to avoid having the compiler see duplicate definitions if we need to include this header file in more than one C++ file. This is the beginning of a camera class. Again, I encourage you to find our DirectX11 math presentation and understand the difference between this XM vector and XM float 3 type. Here we're using the XM vector because we're going to do some math operations likely on these properties as we change the orientation or move the camera around. So we have a camera that has a position, a look at point, and an up vector. We also have a field of view, a near and far clip plane, and a screen width and screen height. We'll create a constructor, default constructor for this camera, and just set some properties that might be typical. In particular, we're going to set the position of the camera to 0 in the X, plus 10 in the Y, minus 50 in the Z. So we're going to move the camera up in the air a little bit and back away from the origin in the Z direction a little bit. We're going to set the look at point to be the origin, and of course we can change this, and then we're going to set the up direction to be the Y axis, same as the Y axis. Notice that these look like function calls and they're underlined, so obviously we haven't written them yet. So we're going to add some additional functions. One that we might need is to get the aspect ratio. We've seen that other places where we may need that. Another one is getting the projection transformation matrix, so we call this function XM matrix perspective. Another one is get the view transformation, and then here is our setter functions for setting the position, look, and up direction. Something else that we might want to add to our math helper, notice in the past when we've converted degrees to radians, we've multiplied by pi and divided by 180. We can start to see that that might be a useful constant to define. So this is not an uncommon thing to go into a math library and notice that they've got constants defined here for infinity and for pi. So we may want to do the same thing for D2R. And that's just the definition for it. We have to actually define this. We actually have to define this as a specific value here in the implementation file. So we've got some capabilities here in our camera class already. Something that we may want to add, another capability that we might want to add is the ability to move forward. So given an amount, some distance that we want to move forward, we could take the position of the camera and move it forward by getting the forward direction of the camera and multiply that by, scale that by the amount that we want to move forward. If we just move the position of the camera forward and don't move the look at point, you can see that that might cause an issue where the camera may actually move ahead of the look at point, and then we'd be looking backwards because the look at point stays the same. So it depends on your application how you want to define what moving forward means. but often you want to move the look at point by the same amount as the position of the camera. So this means we need to be able to get the forward direction. And that can be as simple as taking the look at point and subtracting the position of the camera and then normalizing it. So if we look at that slide in our presentation, what we might be doing here is getting this look at point and subtracting from that the position of the camera and then normalizing that displacement vector to give us a forward direction vector, which will have a length of 1. Once we have that direction vector, then we can scale it by the amount that we want to move forward. Also notice that if we were to pass in a negative amount, the negative of moving forward would be moving backwards. So this is a nice feature that we can take advantage of. So one of the next things that we may want to do, in addition to moving the camera forward, is to be able to rotate the camera so that we could look left and right. And so it's common to rotate about the up direction and then use a certain amount, a certain angle. And I like to, in a lot of my interface functions, work in degrees. I understand 45 degrees and 90 degrees better than I do pi radians and pi over 2 radians. So I like to work in my interface functions in degrees and then just make sure I convert them before I call the library functions. If you recall, in order to rotate the look point about the position of the camera, so in order to rotate the camera properly, we have to take this look point here and rotate it about the eye position. And the eye position in general will not be at the origin. So again, we covered this in more detail in the math presentation, but what we have to do is to rotate this point about the eye position. So this is a general problem of rotation about a pivot point. And what it involves us doing is to translate the problem to the origin, do the rotation about the particular axis, and then translate the problem back out to the position of the camera. So it's a 3-step process involved, and the code for this looks something like this. We create matrices for the translation into the origin and the translation back out to the camera position. We also create a rotation matrix about a particular axis. In this case it'll be the up vector, and then we create a matrix sometimes called C, or doesn't matter what you call it, it's a composition or a combination of those 3 transformations. So here is the translate in. We're translating to the origin, so we're translating by an amount that's equal to the camera position scaled by -1. So it's minus camera position X, minus camera position Y, minus camera position Z. That moves the position of the camera to the origin. So now the problem is translated to the origin. Now we create a rotation matrix about the up vector, and it is the amount in degrees times our degrees to radians constant, and then we translate the problem back out using positive position X, position Y, position Z. We combine those transformations together, and then we transform the look point by that combined transformation, and this will give us a rotation capability. Notice that I've put all of this in the header file. All these functions are fairly small, so we might get some performance advantage if the compiler can optimize these with an inline function call. If these functions were a little more complex and maybe more likely to change, it would probably be useful to put them in their own CPP file. But if they're small and not going to change that much, we can just leave them in the header file. So now we have to go back to our application class and make some changes, because notice that the screen width and screen height are in the camera class, and the camera position is in the camera class. So we need to make these associated changes. I guess the viewport is still in the application class, and that's okay. I don't really see any changes to the viewport based on user input that would modify the camera properties, so that's probably okay. So if we just try to compile our application CPP file, we should be able to find most of the errors or most of the things that we need to change. Sometimes the errors will tell you what you need to change. So in this case, we're setting the screen width and the screen height. So maybe we want a capability in our camera class to set the screen dimensions. So we want the screen width to be equal to the argument that's passed in, and we want the screen height to be equal to the screen height argument that's passed in. And this is a common technique that I use so that the argument name doesn't get confused with the class variable name. We just use the same name but prefix it with an underscore. It's a fairly common programming technique. If you don't, if you accidentally use the same name, you can run into some issues where the argument name overrides the class name, because when the compiler does its scope resolution, it looks for the innermost variable in the scope and resolves the name that way first. So to avoid the conflicts, I always try to use a different name but meaningful and similar. So this technique works out fairly well. So now we want to create a camera in our application, replace the camera position and the screen width and screen height and some of the others with a camera. So now we have a camera variable to replace some of the others that we had in our application class, and we can set the screen dimensions with that. And then we may also want to set the position, look, and up. But we recall that we have a default position, look, and up, so we can take advantage of that as well. So our constructor here has a default position, default field of view, default near and far clipping planes. So if these values are okay, we don't have to change them. So then the next part here where we adjust the window size, we need to access that from the camera. And I made the camera variables public, so we should be able to write camera dot screen width, camera dot screen height. Same thing here. In the update, if we press the down arrow key, maybe we want to back up. So remember, we could use the up down arrow keys to move forward and back. So we can replace this code with the camera function to move forward. And we may want to move forward by some small amount. Something like that. We can change that. And then of course if we press the down key, maybe that's a backward movement, so we just put a negative sign on it, and that might move us backwards. Here we're setting the look and the up and getting the view matrix, and I guess there's no real need to do that in the update method. The camera class is keeping track of that and giving us that capability, so we can remove this for now. And then when we go to render, we need to get the view matrix. So before we draw anything, remember this view matrix is not set, and the projection matrix. We need to get the projection matrix from the camera as well. So let's see where the projection matrix is set. And actually, let's go up and remove these. That might be the best thing to do. So here we're setting them all to the identity matrix. We're not going to worry about doing that. Each object will have its own set of world transformations, and then the camera is keeping track of the view and the projection for us, so we can get rid of those for now. So this is in the render. So this may be a good place to get the view and the projection matrix. And because we have a camera class, we can just say camera dot get view transform. Camera dot get projection transform. So there's the view matrix, there's the projection matrix, and in this case the world matrix is just the world matrix for the first triangle is just a scaling. For the next triangle, the world matrix, which we don't have anymore. So if we need to combine several matrices together, we need a place to put it. So maybe we'll create a variable for world matrix. And we set it to a combination of scaling, rotation, and translation. And then we multiply them all together, world view and projection matrix, to send to the shader. We still have some places with screen height. So here we had an aspect ratio within our application that's been moved to the camera class. So we can remove that. And then on the resize, we need the camera screen width and the camera screen height. And this is in, again, this is in resize as well. And then we're creating the projection matrix here, which we're going to, we've moved to a capability of the camera class, so we can take that out. So this is when we get a size message, so the user's resizing, we want to call the camera class and ask it to set screen dimensions to screen width and screen height. So if we've done everything right, we get almost the same program that we had before, except that notice that the objects appear smaller, and it also looks like we might be looking down on them a little bit, and that's true because we set up the default camera to be further away, further back from the origin, so the objects appear smaller, and we move the camera up about 10 units in the y-axis, so it's where we're looking down at them. If we want to move forward, I will press the forward arrow key, and I'm not sure if anything's happening or if it's happening really slowly because we have such a high frame rate. So it could be that we're moving, but we can't tell because we're moving really slowly, meaning that in the update function our delta time variable might be really small, so that when we multiply 0.1 times something extremely small, we're not moving. Let's just verify that in the debugger. So I'll run this and then just press the up arrow key one time, and we're stopped here in the debugger. And you see that the frame time is really small. It's 4/10,000ths of a second, so we're not moving very far, right? So maybe we want to move 1 unit every second. instead of 1/10 of a unit every second. Now when I press the forward key, still seems like it's not moving very much or at all. So again, we might want to debug this and see what's going on. So I'm going to press the up arrow key and we get here, and again, that's a very small amount that we're moving. And let me just step into the move forward function, and the position, you can kind of see the position here as this would be X and this would be Y and this would be Z, so minus 43. So we started out at minus 50 and now we're at minus 43, so it looks like we are in fact moving forward. And as I step over that code, you can see that the value changed again. So it looks like we are moving forward. It's just maybe too slow still for us to be able to see it. So maybe we should move 10 units every second or more. We can start to see it, but it's still really slow. So let's move even more. And this will vary. You'll have to play around with this depending on your scene, depending on the size and the dimensions of your scene. So we're going to move 100 units every second, and now you can see that we're moving forward and backward, and maybe that's too fast. But there's our camera moving forward and backward. The other thing we may want to do is add in the rotation, which would be the left and right arrow keys. So that's VK left and VK right. And instead of moving forward, we want to call the rotate function and how many degrees. So maybe we want to rotate 180 degrees per second. So maybe 180. And then the question is, should it be positive or negative? If I press the left arrow key, will that be a positive rotation or will that be a negative rotation? And the way you can tell is to remember that we're using a left-handed coordinate system, so it's such that Z is positive, Z is forward. So if you take your left hand and you point your fingertips, not your thumb, but you point your fingertips down the Z axis and curl them toward the X axis, your thumb wants to point up in the air, and that is a positive rotation. So it's clockwise looking down. So if I press the left arrow key, do I want to look from the positive Z-axis toward the positive X-axis? That seems like that would be looking to the right to me. So it seems like that's opposite. So I'm going to put a negative sign for a left input and then a positive sign for a right input. So I'll move a little forward, and then if I hit the left arrow key, you see how I'm looking more and more to the left until everything goes out of the field of view. If I hit the right arrow key, I'm looking more and more to the right until everything goes out of the field of view. So it looks like I've got some really basic camera control working so far. All right, the next step that we want to do is to combine vertex and index buffer and transformation, world transformation capability into its own class. I refer to it as a polygonal object class. So the polygonal object class will have a vertex list. In this case, we've got an image of a box. Maybe in the example code I'll make a pyramid or something. We'll have a vertex list, we'll have an index list, we'll have a DirectX11 vertex and index buffer, and we'll have a list of transformations. Notice that one of the triangles had a scaling and a rotation and a translation being done. We want the capabilities to add a vertex, an index, maybe add an entire triangle. We want the ability to add a transform and maybe compute a composite transform from the transformation list. And then, of course, we want the ability to create and destroy the DirectX objects, and then we could call render, make it the responsibility of the polyObject class to render itself. So a little bit of list of things to do. Let's see how much of this we can do. Again, we'll start by creating a new header file. And in this header file, remember we put this in the source folder as well, in the header file we will create a polyObject class, and this polyObject class will have a vertex list, it'll have an index list, it'll have the vertex and index buffer, and it'll have a list of transformations. And in order to get the vertex position color, I think we'll need to include the may be useful to make another header file. Since the polyObject class will need to release DirectX objects and need access to the vertex position color, and the application class will need to release DirectX objects, it may be useful to put this and maybe this as well in a separate header file. So it might be useful to create another one DirectX11 utilities.h, something like that. And then move at least these couple of things here. And then put the DirectX 11 include here. I don't think we need all of this, but maybe these couple of lines. Maybe we need the math helper as well, so we can get the DirectX11 math maybe. So that might be a good start for this DirectX util.h. And that means we can include it and then also include it in our new polyObject class. So then that means that we can take the index buffer and the vertex buffer and move it to the polyObject class. And then the last thing we'll have here is a vector, and this is not a 3D vector like XYZ vector. This is a standard template library vector, as in a dynamic array of objects for a transform list. So if you recall, we had two different triangles, and one triangle had just a scaling transformation applied, while the other triangle had a scaling and a rotation and a translation. So by having a vector of transformations, we can have a variable number of a different size, a list of transformation matrices. We'll define a default constructor and a destructor, and in particular we've got this destroy DirectX objects, so we can kind of predict that we'll need to be able to destroy some of these DirectX objects. Let's make an implementation file for this class. It's not finding that. And in this case, for the destroying of the DirectX objects, we just want to release the index and vertex buffers. So one of the next capabilities that we want to have is to be able to add a vertex. So we're adding a point at a triangle, and then maybe add a triangle by specifying 3 vertices if we happen to know them all at the same time. So this may be some useful capabilities. code for adding a vertex is extremely simple. We just take the vector of vertices, and again that's the standard template library vector, and we push back the vertex that's passed in. We can do the exact same thing for the index list and push back 3 indices that make up a triangle. And then when we add a triangle, we're adding 3 vertices at the same time, and we need to keep track of what the index list is. So before we push back any vertices, we get the size of the vertex list, and that's the beginning index of the next triangle. If we're adding 3 vertices, so say for example there's one triangle already in the vertex list, so that would mean that if there was 1 triangle in the vertex list, then that would mean that the vertex list has slots 0, 1, and 2 that are filled with vertices. And so the size of that vertex list is 3, and that just happens to be the starting index of the next set of triangles, or the next set of vertices that we may add for the next triangle, which would be 3, 4, and 5. So before we push back any vertices, we store out the starting index, which will be the size 3, push back the vertices, and then push back the indices for those 3 vertices which will be added, which would be the start index, which was 3, and then 3 plus 1, and then 3 plus 2. And now we have added the second triangle both to the vertex list and to the index list. Something else we want to be able to do is add a transform and get a transformation. So here we're just getting a transformation matrix, we're passing in a transformation matrix, and we're pushing it back to on the transformation list. And here we're getting a transformation based on an index. So for example, if one of our transformations in the list we wanted to update, maybe it's a propeller rotating or something moving, we could store the index of that transformation and update it if we could access it. And if we access it by reference, returning it by reference, that means we can change it. So those couple of functions are useful for us to be able to add a transformation and get access to a particular transformation. And I just need to put their prototypes here in the header file. Something else related to the transformations that would be useful is to get a composite transformation. And so in order to get a composite transformation, we have to compose or multiply all the matrices in the transform list together. So we start out with an identity matrix, and then we have a loop that goes through all the transformations in the list. In this case I'm using a range-based for loop. And I'm taking the initial transformation, which is the identity, and multiplying it by the new one and then storing that in the composite. Then the next time in the loop I'll take the previous transformation, multiply it by the new one, store that in the composite transformation. And this way we're building up a transformation. It's kind of similar to how you might sum up a variable. You initialize the variable to 0 and keep adding to it. In this case, because we're multiplying, we initialize the product to 1, or the identity matrix, and we just multiply in the loop. And again, we need a prototype for this function. One of the next things that we need to be able to do is to create the DirectX objects. So here we're going to create a function called create DirectX objects. We pass in the device, and then we're going to take the vertex buffer descriptor and fill it in, and then create the vertex buffer, and then create an index buffer descriptor and fill it in, and then create the index buffer. So it's the same set of code that we've seen before. We're just organizing a little bit better into our polyObject class. I'll just run this through the compiler and see if we have any issues. And then after we've created our DirectX objects, we'd like to be able to render them. And the code for render might look something like this. We pass in the device context, set the vertex buffer, set the index buffer, and draw the index primitive. In this case, it's a list of triangles. So now we have almost everything we need for creating a separate polygonal object with its own index buffer, its own vertex buffer, its own transformation list. We're just not actually creating anything just yet. So we're not creating a triangle, we're not creating a box, we're not creating some type of object just yet. So let's go ahead and do that. We'll just write some function that creates something. Create a triangle. And by creating a triangle, we mean filling in the index, the vertex and the index buffers necessary to create a simple triangle. And so to do that, we can call our add triangle method and pass in three vertices. And so maybe we want the first vertex to be at the origin and it to have the color red. So remember that the structure for this vertex is position color. So an XYZ position and then a RGBA color. So here's the XYZ position. And then here's the color RGBA. So it's positioned at the origin, the first vertex, and the color is and in order to complete the add triangle, we have to add 3 of these. So maybe we want to put the next one 10 units down the x-axis and then the next one 10 units and the y-axis, and we can vary the color if we want. Change the color for each of the vertices. So we've got the first vertex at the origin, the second vertex at 10 units down the x-axis, and then the last vertex at 10 units in x and 10 units in y. I think that's similar to what we had with the other one. So if we create a poly object and call create triangle, and then call create DirectX objects, and then set transformations, and then render it by getting the composite world transform and then calling its render function, we should be able to see triangle and be a little bit better organized in terms of our code. So this means that in our application class, in addition to a camera, we're going to need a include for the poly object, and we're going to need to define a poly object. I'll just call it triangle 1. And if we compile our application program, we can find the errors and hopefully find everything we need to change. In particular, we no longer have a vertex buffer and index buffer, but we'll notice that they're being set to null. That's probably a good idea for us to add to our constructor, our default constructor for the poly object. That's probably a good idea to add those initializations. So here in the render, this is where they're set, and it looks like this code is in our render for the poly object, so it looks like we can replace this code with triangle 1 dot render and pass in the device context. And actually, that is here probably the place to do it. That's where it actually gets drawn. So we're setting the transformation. Now, something else we want to change is we want to be able to get the transformation from the triangle itself. So in this case, we want to change this and get the world transformation from the triangle. So this scale will be added to that triangle class or that triangle object. Right now we're not going to have a second one. We'll just leave this out and just do one triangle for now. So here are a list of vertices that we had and a list of indices that we had for the triangle. We'll take them out. And then this is the vertex buffer and index buffers that are created. We'll take them out and we'll replace this with triangle 1 dot create a triangle and triangle 1 dot create DirectX objects. So we're creating those objects. And we may also want to set a transformation here. Add a transform. We had a scaling transform, but don't see it, so we will use XM matrix scaling and pass in a scale factor, which I think for the smaller one we had 0.1f. So our steps then are to declare a polyobject variable, we called it triangle1, call the function that actually fills in the vertex and index buffer, call the function that creates the DirectX vertex and index buffer, add a transformation, a world transformation, and then when we go to render, we get the world transform from the polyobject class and transpose it and combine it with the view and projection matrix, transpose that result and send it to the shader. And then we call a triangle class to render itself. So I got some warnings about not using this in the world matrix. We're not using right now, and the T we're not using. So these are going to be in these matrices are going to be in the polyobject class, so we can remove them. And the message string, I guess we're not using this right now either. So you can see that we have a really small triangle off in the distance. We can move forward and see a little better maybe. Maybe we're moving a little bit too fast now, but and our triangle is scaled really small. So if we can find the scaling, seem to find it. Let me go to the application class. And maybe change how fast we're moving. It seems like we're moving really fast as well. There's our triangle. We can move forward and back and look left and look right. And I think we'll end this presentation here. It's almost an hour long. We had a lot of code to cover and go through. So we'll end this here and do a part 2 of this presentation. And in part 2, we'll create a second object and maybe even an enclosed object like a pyramid or a box or something, and also talk about what strategy we could use to make a terrain or a ground. So let me know if you have any questions on this presentation, and also be on the lookout for part 2, and also be on the lookout for the DirectX11 math presentation.